Hi, in the last tutorial, we covered the basics of SolidWorks simulation. In this video, we're going to dive into the theory and practice of material selection, the ways materials affect our simulation results, and how we can edit our part geometry and material selection to have better simulation results. This is going to be a very material-focused lesson, as material selection is an often esoteric subject, but crucial to good part manufacturing. So here are the primary properties that I consider in my material specification. Vicat softening temperature. This is a great way to get a base feel of a material. This test, the Vicat softening temperature, is a test which involves taking a 1 millimeter cross-section needle with a flat end and pushing it to a depth of 1 millimeter into a said piece of material, a given piece of material. And the temperature at which the needle penetrates the material to a depth of 1 millimeter, that temperature shows the Vicat softening degree. So a material with a temperature that's very high means that the polymer needs to be at a very high temperature for the needle to penetrate it. Now, if your Vicat softening temperature is very low on a material, it means that it's very easy for the needle to penetrate. And so the material temperature can be very low. And so what does this say about a material? Well, the thing that it shows is if a material can be penetrated at a very low temperature, it also means it can be molded at a very low temperature. It means that the mold cavities may not need to be heated that much for proper injection. Likewise, if the temperature, the Vicat softening temperature, is very high on a material, it may mean that you're going to get short shots unless you have enough pressure and enough temperature in the mold to push the material in. There are two different tests for Vicat softening temperature. One of them is a load of 10 newtons, and the other one is a load of 50 newtons. Here's a way I think about it, and this is the way that the test machine, in theory, actually works. There's a pin, as I mentioned, with a 1 millimeter cross-section, which pushes into the material. On top of it, there's a weight. For Vicat A, it's 10 newtons, and for Vicat B, it's 50 newtons. And the weight is placed on top of the needle, and the needle presses into the material to determine the Vicat softening temperature. This is the second sort of specification test that I like to look at when I'm looking at different materials I want to use for different applications. And it's called melt flow rate. Now this test is a little bit different than the last. And the difference is that in this test, you're taking a polymer and you're placing it inside of a capsule. So what we're seeing here, this gray section, is really just a metal tube. That's all it is. And this red section, which I've illustrated, is a heating element. It's a constant temperature throughout the entire time of the test. And on top of our material here in yellow, we have a weight. And this weight pushes down on the material, and the material is forced to flow through this orifice. And this test really is just measuring how many grams come out in 10 minutes. So as you can imagine, a material that has more grams that come out in 10 minutes will have an easier time coming through the nozzle of the injection molder. And of course, as we can imagine, if the grams per minute is lower, we're going to have a harder time forcing it through. And this can as I've mentioned before, create short shots. It can create problems in the mold where the mold maybe fills 99%, 80%, something like that. Or it may take longer for the material to fill the mold, and there could be other complications. So here's an example of a test I did and some information, and this model is the same model that was shown in our previous test that we did in our introduction to Solidworks Plastics. And so for this test, I chose this material, Geloy Resin XP4025. It's a PCASA. And the Vicat softening temperature on this material is 109 Celsius. And I'm using the rate B Vicat softening temperature for this one. So that's 50 newtons of a weight to push a 1 millimeter cross-sectional needle into the material. That's the test. And before I get to some of the other specs, I'd like to touch on injection location. The injection location for this part is at the tip here. And you can see that the simulation is asking for 9,297 psi. And because of the fact that the injection location is here, you can see that there's a lot of pressure in this area for filling and very, very little pressure here at the end. There's actually 0 psi in this region. The weld line propagation looks the way it is, with weld lines in the middle of the ribs in a dangerous area because of the location of our gate. There's also a lot of there's a sink mark deformation here that you can see coming up as well. That being said, the melt flow rate is only 18 grams per 10 minutes. Now, what that means is that this is a pretty low melt flow rate. And a pretty low melt flow rate is going to make it hard for the plastic to come through the mold. You can see in this example that the material doesn't have much of a problem in its beginning when it comes in at this gating location right here, but it has a lot of time coming all the way to the end. And if we look at these clamping force here, you can see the amount of pressure that it takes for every fraction of a second to actually push that material in. And the fill time for this part is 0.969 seconds, with a melt temperature of 271 coming out of the nozzle. Now the wall thickness on this part is 0.062. And I've listed some machine properties here, but this isn't really relevant necessarily. This is really just a baseline example. This machine can definitely create this part, but what I'm trying to show with this example is a part that maybe is not designed that well. We have our injection location in this spot. We have a wall thickness of 0.062 that's very thin. We have a material with a very low melt flow rate and a very high Vicat softening temperature. So it's very truculent to work with. Now let's switch to our next example where I've reworked the simulation and run it again. You can see in this example, I'm using this material. It's also an ASA PC. And the Vicat softening temperature is at 105. In our last example, if I go back, it was at 109 Celsius. So a very slight difference there. Now our melt temperature out of the nozzle is 260 to 280. In our previous example, it was 255 to 270. So it's actually hotter melt temperature. But the big thing to note here is our melt flow rate is 45 grams per 10 minutes. That means that when you put this in the tester that we saw in the first example, now let me go back to that. When you put it inside this tester, you're going to have 45 grams coming out in 10 minutes. With our other material, there were only 18 grams coming out of the orifice. That says something about the viscosity of the material and how easy it flows into the mold. Not only that, but in this example, we've upped the wall thickness, which leaves a larger area for our material to flow. In addition to that, I've made a change to the injection location. The injection location is now here on the side. You'll see that the PSI it's asking for is 4,309. In our previous example, it needed 9,297. This is way more taxing on the machine. It uses more electricity. It's harder on the machine. In this example, it's much easier for the machine to push the material in. And you can actually see that the fill time is different. This is 0.899 seconds. In our other example, it's 0.96 seconds. Now, not a huge difference, but it is a different amount of fill time, and that's going to have an effect on our part. So the main takeaway that you can see and the great result is the fact that here on this end area where we were having problems before, you can see that there's 2,320 psi. Now that's a great sign. That means that we have pressure more evenly distributed through our part. This is mostly in fact to the location of our injection gate. Now that's going to help us a lot because that's going to really reduce the effect or the probability of a short shot. Now in our previous example, having 0 psi at the end is a major problem. The material is going to have a very hard time coming through here, especially with a wall thickness of 0.062. As I mentioned before, our wall thickness is much higher in this example, and that makes it easier really for everything to happen. Also, our sink marks are reduced. This is 0.01 in this example. In our previous example, it was 0.015, so definitely higher. One of the last things I'll touch on here is the weld line propagation. Now, this is all to do really with gating and not much to do with the material itself. In this example, you can see that the weld lines are in between the ribs. This is really bad because the ribs now have a weak spot right here in the middle. They can easily break. In my example, after, the fact that I moved my gate location to the side has created weld lines here more on the fillets, which is a much safer place to have them. Now, you can't really get rid of weld lines. Anytime that you have a pin in a mold or a piece of a mold where the material needs to flow around that pin or that insert, you're always going to have a weld line. It's just a question of the angle at which those two cold fronts of material meet, as well as the location that they actually form. And we've been able to move the location of the weld lines by changing our gating location. So these are some of the things that are great takeaways in SolidWorks simulation. These are the sorts of factors and specifications that I look at when I look at material selection. If you have any sorts of specifications that you like to look at when you're choosing different materials, definitely let me know in the comments. I'd love to learn about your methods. Thank you.